Hey, thanks you guys. Thank you all very much for coming. My name is Denise Gosnell. I am a former data scientist, now technical evangelist for PokitDok. Absolutely love my new role because I get to basically make it data science and attending things like this. So it really is some of the best job I could have. I'm here to talk about my experiences that I had while a data scientist at PokitDok, and specifically when I was building backend engineering initiatives with graph databases and then eventually relational databases and then other things along the way. So that's kind of the theme of where I'm going with my talk. My background is I started off in mathematics with an undergrad and a master's, emphasizing in first cryptography and then graph theory. My PhD was in computer science where I did social fingerprinting across the telecommunication industry. So there's a lot of really interesting information to delve into for any kind of coffee chat if you want to chat later. But as far as today goes, I'm not going to go off on either of those topics. We're going to talk about the differences and the benefits of graph and relational databases. Before I go into any of that, who uses graph databases right now or have? Okay, how about relational? All right, we are skewed. Okay, well, I'm sure you already heard I'm a graph theorist at heart, and I might be leaning one way or the other, but we'll figure that out as we go. Just to kind of set the stage on the type of data I'm working with and the perspective I'm coming from, PokitDok is the API platform for healthcare transactions. So like Twilio does with communications or Stripe with finance and whatnot, that is exactly what we provide for healthcare. And just the kind of the obligatory, where is this getting used? No, I did not normalize by population on this map, but that's because it has yet to be a population map. So I find this to be informative to see which employer groups across the United States are starting to adopt more of the health tech or telecommunications type of sectors. So this is kind of by county, the number of transactions we process across the United States. I hope to normalize it by population one day. That's my goal. But to get to know healthcare data means you have to be able to read this. And this is an ASCII X12 eligibility request. That up there in front of you is asking, am I eligible to receive a chiropractic care from some doctor has your back? Can I get a chiropractic visit with him? And the ASCII X12 spec, it's 552 pages just to ask that question or other types of questions you can when you're just trying to figure out if you're eligible to get care with that doctor. We translated that to JSON, and that just makes API processing a lot easier. The reason we really wanted to translate that to JSON is that there's one company that exactly, not one company, but if you're going to process Medicare, you have to abide to the T to this spec. Everyone else, it's loose. So the back switch word of communicating with every insurance company in the United States is not fun. So once we send this to any insurance company in the United States, this is what they give it back to us, and then we translate it back into JSON. So for eligibility, for filing a claim, for billing, scheduling, any type of touch point when you go to the doctor, we have an API for it. Okay, business pitch over. What is really useful to me as an engineer, as a data scientist, when I'm working with this JSON and thinking about all the interesting data science models I'm going to build with it, we then, of course, you can imagine all of the beers and the fights that happened over how are we going to store this data. And we kind of settled on a, well, what problem do we want to tackle first approach? And so when I came to work with PokitDok, I think in August of 2014, the problem we wanted to attack at that time was, all right, let's just find, identify, and recommend similar doctors that we're processing within these API transactions. So we're seeing a consumer go get care with a doctor, and then they file a claim with a doctor. Through that touch point, can you just make some recommendations, really simple recommendations? I'm a graph theorist. This cannot be a surprise that, of course, I wanted to solve this problem with a graph and graph databases. Let's just jump to at least one conclusion. This result. This right here is the Medicare referral network across the United States. The vertices on this graph are doctors. The edges between the vertices are if that doctor saw 7 patients or more in common. Because working in healthcare, I have this big cloud called HIPAA over me, and I cannot do anything that would release your identity. So we have to always do everything in aggregates. I never can know a single person. So On the aggregate, the thinnest of edges is 7 or more patients. The thicker the edge, the more patients. The colors of the nodes and the size of the nodes are the other two things to consider. Color is just a network algorithm that I ran to kind of detect optimal communities, but I'm not really concerned with color, I'm concerned with size. The size in this image represents the amount of money that that doctor received back from the government in Medicare reimbursements. Down there in Florida, we've got some problems. Those 3 doctors in Florida, each I think got back 7 million, 12 million, and then 20 million in that one calendar year for Medicare reimbursements. Good news is we found them and they have now been put in jail. So 6 months ago in July, not we as in PokitDok, I mean the community. I would love for that to be my thing, so I did not mean to imply credit. We essentially found out, the community that is, that there was an illegal billing scam going on down in Miami, where they were using your doctor's NPI, which is essentially their social security number within the healthcare system. They were using their NPI to illegally bill pathology, which pathology is getting blood drawn and whatnot. So they were just billing it over and over and over to illegally get reimbursements for pathology. That was 6 months ago. So it's pretty interesting to get to immediately just model something with a graph and get a result that is so obvious. We saw a lot of these graphs. This final one was the best one. You know how that goes. But we're an API platform company. It was really interesting to model it. The problems I need to solve are I'm processing hundreds and thousands and up to millions of transactions on different windows of time, and I need to persist them, and I need this to be scalable. So when we started off about 2.5 years ago, we started with doing the API event streaming with Kafka. Throughout all of our engineering, that is the only thing that is maintained, its stability to be able to handle everything. And we started off with Titan, backed by Cassandra, and we were trying to do basic recommendations and similarities using our traversals. The graph theorists in the room were like, yep, that makes sense, it's exactly what we do. So for the people who don't build graph databases every day, graph people, gonna need a few minutes. But for building a graph, when you think about modeling your data, think about that JSON response. You're filing a claim about a person to their insurance company about their interaction with a doctor. So there's 3 people, but then there's also the service that happened. Say it was just a chiropractic adjustment. So when you process the transaction, I modeled this with these 5 basic entities, and those edges represent the ground truth of what we actually observe. An eligibility check gives you kind of a good idea of the fact that not everything I process can be ground truth. A lot of people process eligibility just to say, hey, am I eligible? Or hey, is this doctor in my network? That does not mean that the person actually got care from that doctor. So one thing that we try and do is use the ground truth data to infer based on visits how we use this ground truth data to identify and recommend doctors based on what we can infer from ground truth and non-ground truth. All right, let's just work on identifying. When I wanted to set up identifying doctors, I started off by making a bipartite graph. I just wanted to look at 2 different types of vertices in the graph, and then the edges only can connect one type to the other, not within. And what I'm going to do is I'm going to think that the purple vertices in this graph are us, they're the consumers, orange are the doctors, and in my graph database, I want to go ahead and be able to recommend a similar doctor according to one doctor. What I have here is Gremlin, which is a Python, or it's a graph query language. In my database, I have selected one specific doctor. What I want to do is I want to traverse the edges to look at the people who maybe scheduled an appointment with or filed a claim against with that doctor. And when I think about this process in graph databases and graph theory, I literally envision myself kind of walking through my data. So when you're doing your graph traversal or graph database lookup, you select a vertex, and now I'm going to walk down the edges that say you scheduled with that doctor. And I'm going to continue the walk to then go back to the other providers that those consumers scheduled with. What we can do at this point is count the number of paths that get us to the different doctors or the different highlighted orange vertices on this diagram. I also don't want to include where I started from. So I'm going to filter out where I started from. I started from the blue vertex. I said, who scheduled with that doctor? Who else did they schedule with? And now I can get a group count and a ranking on a similar provider. So the number of paths that you can get to that orange vertex immediately next to the green, there were 2 different ways to get there. It's a way to identify similarity. I love graph databases because you can explain it with pictures and walk through your data. I'm glad you think that's good. But what I also want to do from a data scientist now is I want to do a point-based recommendation. I'm going to go for the same model. I might have a web portal up where people can browse doctors and they can maybe look at a few doctors. So again, you're the purple. You've now browsed 3 doctor profiles on either your insurance's portal or the old PokitDok.com. And what I want to do is I want to use the information about which doctors you viewed to recommend someone else outside your set that maybe you should also take a look at. In a graph database, you would go down to the doctors you viewed, and you could then select the edges of people that were previously scheduled with those doctors. Viewed, scheduled, and you can go back down to viewed again if you would like, or a different type of edge. But what we're going to do in the end is, again, apply group count, which essentially is counting the number of paths that got you into this new set of doctors. Rank them, sort them, and I can return this guy with 4 votes to the user in the front-end interface to say, this one is the most likely, according to all the other data I have, this one's most likely to be a relevant doctor to whatever you're looking for. I have all these slides up. This coding language I have down here is Gremlin. It's adopted by Apache Tinkerpop and the Titan community. So it's a very interesting way to kind of get a graph stood up, walk around it, try some queries, see how it goes. And we were just talking about this. When I first looked at this database, and this is not rendering very well on, let's see if I can get it here. Here we go. So I set this up. We had a marketplace online that anybody could look at and browse any doctor in the United States. And that is what you're looking at here. The goal of this model was to identify and recommend similar doctors. From our database, I pulled the top 100,000 most active, or the people who looked at the profile the most. That was the first metric of my prior I was putting into this. Just looked at the most viewed. After I grabbed those doctors, I wanted to create a graph to see how they were similar. The blue vertices on this image are all of the doctors. The yellow vertices represent their specialty within healthcare. And if they have a common specialty, there's an edge between themselves and the specialty. When I'm looking at this image, knowing that these were the top 100,000 most viewed doctors on our forward-facing application, I see 2 things. I see a hairball kind of in the lower right, and then I see that really large yellow circle up in the upper right. And those are the really 2 clusters that I wanted to focus on. And it made me it was very grateful to see this in the results. When I went back to see which doctors were down here in that section of the image, this one down here, so I'll use the screen, that the hairball doctors, that was kind of your internal medicine, or it was your primary care, it was the general practitioners, it was the nurses. Those people you probably remember most frequently interacting with in your own personal experience in healthcare. But this image up here, this subset, this cluster from my graph database, that large yellow vertex represents the specialty of behavioral health. And the group of doctors related to behavioral health, counseling, marital counseling, other types of therapy, that was the most viewed and most scheduled with type of provider on our system. And that was really exciting to me. It was exciting because the last time I went out and talked or asked my friend for a doctor recommendation, it was about family practice or my knee hurts, send me to a chiropractor. But to see that in the health tech industry, that the immediate application of this was to help out people looking for behavioral health, where there's kind of a stigma of asking your friend, hey, I need a therapist. It was kind of exciting to see that come through in our database and in what we were processing every day. But let's be honest, I don't know if you've kind of been tracking the types of words I've been using. I keep talking about the graph we had, the database we used to use, and the processes we used to run 2.5 years ago. About a year ago, we had to tear this down, and it was probably one of the saddest days thus far in my engineering career because I put so much heart and soul into this. For your architecture and implementation of graph databases, it really just depends on your application. And we started processing so many API requests for being able to do eligibility and claims that we were breaking everything we kept trying to throw at it. We broke Neo, we broke Titan, we broke DataStax Enterprise. We just never were able to find that right application or that right infrastructure to handle our heavy writes that would scale with where we were going with our platform. And as you all know, just like any other area, there's not really one database that is going to rule them all. There's a lot of options and a lot of different types of graph infrastructure out there, each of which are going to give you the ability to solve your application within their realm. But there's really not that one thing that's going to solve all of our graph problems. But as you all can tell, one of my favorite parts about graphs, and you all know, the visualizations are amazing. Whenever you run a static model and you get insights, it's probably one of the most powerful things you're going to be able to get out of using a graph model. As far as what I used up here, Gephi is the way to go. And then for some really cool interactive graphs on a smaller scale, I used a lot of D3. But I did promise to you all that we would kind of cover graphs and tables. So what I want to move on to at this point is a different problem. And that problem would be, how do you kind of group our transactions together? We're an API company. We're processing all these different types of transactions every day. I just want to know which ones within a certain API are similar. That is when we had to move and transition into using relational databases for this. So right now, for solving this type of problem, we're still using Kafka. It's processing all of our streaming events throughout our entire back end of our system, and they're persisting them to a MySQL DB. Makes me cry a little bit as a graph theorist, but you know what? As you'll see, there's a lot of really good things to do, a lot of really good things coming out of this. After we're persisting them to MySQL, as you'll see here, there's a lot of models you want to build, and we do have to pull them back offline for some batch processing and then kind of get them back integrated into the system. But let me dig into that. So bringing back to the type of data we're working with, we're using JSON. And I just told you that we're using MySQL. What? JSON into tables? No, I'm not talking about Mongo. Let's not go there. So just like anyone else who has approached the problem of building a relational schema in your system, we now had to look at what type of JSON we were processing, and we had to say, all right, we need a transaction table to represent the transaction within itself. We have apps that can build stuff, so we need an application table. We need an API table to track our versioning and all this stuff. So that's where we started, just like anyone else who goes down the relational path will go. I knew zero SQL. I picked up Gremlin like a charm. Had to work on SQL, and that was a new thing for me. Basically, when you're writing select statements or when you're writing SQL queries, as about 80 to 90% of you all know, you're going to select information from a specific table. You might need to join it with another one, and you might want to group it according to some constraint. Really high level. But with this infrastructure and switching over to MySQL, the most beneficial part about this was our development time went from about 1/10 of what it was to get our graph database completed. And every problem we had, someone else had already solved it probably 5 to 10 years ago. So it was really quick to get up a really nice interactive dashboard. So what I have over here, and really not well zoomed, and I think my zoom might mess this up. I'm sure many of you all have seen these within your company, but within a month from switching from using a graph database to using a relational database, we were able to get all the engineering done for indexing, schema, all that stuff, get your database stood up, but then also we built a really quick dashboard. Now, insert name of company that does this for you: Periscope, Tableau, Pentaho, there's a dime a dozen. But on the other hand, it was pretty easy to kind of write it real quick with JavaScript and D3. So that's what we have here. And to me, one of the big benefits, and yeah, you're looking at our production data of what we processed in the past 14 days. And it was so easy to get to build all of this so quickly and then get to a point in which you can derive insight from your data. But not obviously, there's going to be pluses and minuses for everything. As soon as we started driving those insights and looking at our dashboard, someone came over to my desk and was like, "Hey, so we've got some apps who are sending in like misspelled trading partner names or insurance companies' names, or they're trying to connect to insurance companies. Like, can we get some analysis on the type of trading partners and insurance companies people are connecting with?" Well, as you all know here now grown, we've got to add a table, you've got to somehow get a foreign key, you've got to rerun, you've got to link, and now we've got to start joining. Oh my God, it was a mess. But it's solved. All of these problems are solved. The development time for getting this done, the resources out there for using relational databases, it's super easy to find it or to talk to someone who can guide you really quickly through the process. Having to add a new table, okay, it's a little annoying, but it can be done pretty quickly. Once you keep adding all of these tables, now you're getting inner join this, left join that, right join that, and your index queries are so slow that it almost becomes really difficult for me to render that other image that I showed you, the interactive dashboard. So you've got another set of problems. Nothing really solves everything. That can't be a surprise to you guys. But I'm a data scientist, and I spent all this time just a little bit ago showing you in a database how you can set up a graph database and find and recommend similar entities within that database. And my whole goal here with switching over to MySQL and using a relational database was to do something to recommend that was at the same cool factor of what I was doing with my graph. And we've got a really cool BI tool, get some great analytics out of it, but where can we get some more useful information? And that is where we had to look at our relational database and say, hey, it's not going to handle it. What you want to do, we need to go out and get back into more language-oriented data structures, like using data frames with Spark or using more matrix-oriented ones. So that is what we did. So we've got Kafka streaming in our infrastructure. It's persisting to MySQL across all of these different tables. And I'll grab a big chunk. I'll write a Kafka stream to grab a chunk. And one of the first models I really wanted to build was finding similar transactions. So I translated our transactions into basically a bag of words model, where you would always start with this. In this example, you can think of document 1 having a member ID in our healthcare data. Their member ID is ABC. Document 2, the member ID is DEF. And essentially, you just flatten out your JSON and create a really, really sparse matrix. If you are interested in having a code that takes JSON-L into a binary matrix, sklearn has a dict vectorizer function that is phenomenal. I think some people have already even found my slides. They're up on GitHub right now with some live links to be able to access this code. So if you want to be able to take JSON-L file, translate it into a flattened dictionary, this will work. The meat of it is right here, is this get grammar function, which, thanks presenter, you didn't put that up on your slides. It formatted terribly on these slides. I have a link to it, the code down there, if you want to actually look at the function that will get a grammar and extract all the unique elements for you. But yeah, so if you're interested in that, talk to me or find it on GitHub. The beauty of taking this approach of following a tabular model, creating a matrix out of our JSON-like data, was that now we're in Spark, now we're in Python, now we've got a data frame. Now it is the world is your oyster, do whatever. And it was really interesting to start to get to cluster it. So let's look at one way to cluster these eligibility documents. Thought LDA would be a really good way to go for it. When you apply k-means, you apply the restriction that your document can only belong to one cluster. But when you're processing healthcare information, you could have a few different topics of what's going on in that data. So I wanted to start with doing some latent Dirichlet allocation on our documents. So for anyone in the room, to kind of get a really high-level understanding of what LDA is doing, let's pretend we have three documents or 3 sentences. I like broccoli and bananas for sentence 1. Sentence 2 could be my sister adopted a hamster. And then sentence 3, look at this hamster munching on a banana. For LDA, it's going to do 2 things. 1, it's going to determine the topics within all of the sentences together. And then second, it's going to assign 1 or more topics to each sentence. So as you're looking at these 3 sentences, you kind of got food as an option. We've got pets or animals as another option. So once we determine those are the topics, LDA goes back and says, all right, sentence 1, 100% about food. Sentence 2, 100% belongs into the hamster or animal category. Sentence 3 is going to be 50% about food and 50% about animals. Really high level on LDA. That's what we wanted to do. So We went back, we grabbed a large portion of our eligibility responses, and then we converted them into different forms of a bag of words model. I did use the flattener from the previous slide where you allowed the key traversal into your JSON to persist in the grammar. But for this example I have on the slide, as you look at an eligibility request, the words of importance in here are coverage, coinsurance, chiropractic. You see that. But think of a word like California. When you are processing an eligibility request, California could be the billing address for the provider. It also could be related to the billing address of your insurance company, or a different state could relate to the person. So to solely extract out California as a true bag of words model loses the importance of how it originated to its representation in the data. So when we ran this model, I did use that code a few slides back. That was the true flattener that kept the location of where that field came from. Has anyone ever looked at PyLDAViz? This has got to be the coolest library I have ever seen. So what we have is, well, let's just look at it. Oh, of course. I hope I'm on the internet. Let me make sure I'm on the internet. 1 second to connect. I don't know why when I clicked on it, it disconnected for me. Don't you love it how you have everything all ready, and right when you go to pull it up at that moment in the presentation, it's going to do that?
That was gone.
You're in the category with all the other very famous presenters.
That's very kind. I do really want to show that to you, so what I'm doing over here is I'm going to get reconnected to our prod database because that's safe to do during a presentation. Of course. I know, right? So the good news is I'm on Wi-Fi, but for some reason that web page decided to no longer load. All right, we are back. Look how quickly it was to connect to our prod data. That was safe. Thank you guys so much for entertaining that. But I really wanted to make sure I showed you the PyLDAViz package. So what we have here is we ran the LDA algorithm across all of our eligibility checks to then optimize for the number of different topics in our eligibility. So grab 100 million eligibility checks and let's figure out the number of topics that is optimal for those 100 million. And that's what you're just looking at here at the left on this visualization. What you can see is we have about, 10 different clusters. And each of these clusters here is represented with a circle. And the size of the circle directly correlates to the number of documents that mapped into that circle, mapped into that topic. And then its representation on the XY axis is the principal component 1 and 2 from the really large, sparse bag of words matrix that I made. With this, it's interesting to say there's topics there, but what I'm more interested in to know is what words are in that topic. And that's where the PyLDAViz library is really interesting to interact with, because you can hover over these topics and get insight into which words are important for each topic. So I'll click on topic 2 and hold it so we can see. Topic 2, whenever I ran this analysis, topic 2, the most important word in topic 2 is hospital, dental, health. So this might be the eligibility checks for dental coverage. What you're also looking at here, though, is that in that hospital bar, you can see yellow and green, just like any other word. The yellow is the count right now for the number of times that term was in this topic, and the green represents its relationship to the entire corpus of documents, everything that's outside this topic. When you're using this library for visualizing LDA results, if you're interested in looking at the words that maybe are more particular to just this topic, you can change your lambda value for the LDA, and it will kind of resort your words so that you now can re-rank them to say, I'm interested in seeing words that were important according to the whole corpus, but had a highest rank for my topic, but then switch it down all the way to say, I just want to know the words that were mainly 100% in my topic. So it turns out, Blue Cross Blue Shield, MA, Maryland? Medicare, something. Yeah, state abbreviation that I can't remember, thanks fifth grade. That particular word was unique to this topic. I believe, and when you click on the words, you also can see which, how they are distributed across all the topics and which topics contain that word. I think topic 6 was really interesting. It was kind of on top of my head for some reason. Oh yeah, topic 6 were psychiatric type of eligibility requests. So this is a really cool tool to play with if anyone does any type of linguistic modeling or LDA or other type of models. It's pretty great. Thank you very much for letting me take the time to disconnect, reconnect, and kind of take a little side topic. So those both were 2 examples of what we were able to build once we moved off of the mindset of graph theory and graph databases, and we moved on to the mindset of let's use existing tech and let's go back to using matrices, what's already been proven to really work. And that has made all the difference for us because the development time for getting things done from an engineering perspective was about 1/10 of what it was before. And we were able to get a little bit further, such as the LDA application I just showed you. We also were able, to make a nice little business analytics dashboard, just getting insights out really quickly, or really cool insights, but they're different. But you all were here maybe because of a clicky headline saying, graphs versus tables, fight! Like, what's happening down there? I'm just up here to present my experience from having written both databases, not written themselves, but implemented both of those databases, excuse me, and then had to derive data science models on top of them. When we were approaching each of the problems after multiple experiences, what I really learned from this process is that I really needed to consider beforehand what my question was, what I was going after, what my real application was, and then approach and choose the tool that was best for the application. So now we're a polyglot house. We've got models that are run. I run models and model them with graphs when they need to be done with graphs. But a lot of our day-to-day operations and analytics are being done in our relational scheme. As you all know, and hopefully for people who hadn't really experienced graph databases before today, graphs are really great for relationships. It's really great when you want to take the Facebook approach of I'm on Facebook, you're on Facebook. There's edges between us if we're friends, edges if we're not. Maybe after this we all can be friends. More edges. Let's give them more data. And even more empowering for me is when you can summarize your data and summarize your model into a graph visualization that really can drive insight. But both of these are one-off models. These aren't things that were working for us when you needed to have a streaming like a streaming architecture for your engineering platform. And that is where bringing in a little more mature technology for being able to handle all these heavy writes and handle our streaming architecture really brought us a lot farther in the analytics to get cooler data science done with doing some really cool really cool feature modeling with doing LDA across all of our claims for eligibility checks. So I don't think I've given you one answer. Hopefully I've given you some ideas on how to approach or pick what, or maybe what you can do with that specific tech. But where you can go from here and where I would love to see, I would love to interact with any of you all on GitHub and or Twitter. All these slides are live now. I'm running them, you can see from my GitHub. If you want to, if any of you are new to graphs and you specifically just want to get a database and try some traversals, thank you. I did not do, as a non-front-end engineer, you can't really tell that I have links here. So I'll try and fix the link color, but essentially all of these things have links here to find them. But our Gremlin Python on GitHub, you can download it. It comes in a Docker container, and once you finish installing your container, it'll hop you up right in the REPL to start some graph database traversals if you want to try that. If you're interested in learning about our experience with Spark or any other infrastructure with Kafka or using MySQL, we put a bunch of discussions up on our blog. We have Python snippets out the wazoo with our snake bites that we do. We really try and be as transparent and as giving back to the community as we can. And the more questions you ask about stuff, the more we might dive into it and then publish our results on our blog. But I just want to thank you guys very much for kind of enduring this little chat today. I really appreciate that you all are here. And please reach out.